dedicated categories. But I might take that off. I've heard you guys say I jumped. Do you have any coding experience? I think quiz results.
All right, good morning, everyone. Let's get started here. We're going to spend the first half of the class finishing off chapter 29. Now we're going to talk about Lorentz force and magnetic dipoles. And then we're going to jump right into electromagnetic induction. That's what we'll spend the rest of the week on. So that'll take us to the end of the course. So just as a recap from last class we spent a good amount of time, well, we started off last class talking about the Biot-Savart law. And the Biot-Savart law basically tells us how to find the magnetic field strength. Whenever you have a charge that's moving, you can find the magnetic field strength. Right? And then if you take the Biot-Savart law, apply this, break it, any current distribution into a bunch of little chunks, add them all up, you can find the total magnetic field. That can be kind of hard, right? So we came up with, we wrote down Ampere's law, which allows you to find the magnetic field of a current distribution when it would be harder to find it using the Biot-Savart law. So notice this is kind of an interesting equation. By finding the line integral of the magnetic field around a closed loop, this circle here is the closed loop. Closed loop. If you just take the line integral of the magnetic field around a closed loop, you know it always has to equal mu naught times however much current punctures the area that's bounded by that loop. Right? So you can think of one particular loop. If I make one closed path that looks like this, this is my closed path. There's different different areas which are bounded by that loop, right? One is just the flat path. Call that A1, but you could also have some other. You could also have a net, for example. Right? And what the Biot-Savart law says is regardless of the area, as long as you integrate the magnetic field around the loop, it's always going to equal mu naught times whatever charge penetrates the area that's bounded by that particular loop. And we applied this law to, this is an integral equation, but we applied it to find the magnetic field in situations which are highly symmetric. For example, that thick wire. The thick wire we know has to have a magnetic field that circulates around, only depends on the radial distance, and we use that to basically take the B outside of the loop here. All right, so let's look at one more example of this, and let's say I have a magnetic field. Let's look at a solenoid. Okay, so if I draw a cross-section of a solenoid, which you can think of just as a cylinder with a bunch of loops of wire that are wrapped around, I get something that looks like this. So on the top section of the loops, I have a bunch of wires that are coming out. And these ones are wired down to the bottom side of the loop. So here I have current going in. Here I have current going out. All right, so this is a cross-sectional view. Okay, now Ampere's law, we can only really use it when our current distribution has a high degree of symmetry. So a finite solenoid doesn't really have a high degree of symmetry, right? Because you could translate it back and forth. And that would break the translation symmetry. So let's just make it a long, very long solenoid. Or in other words, the radius is just very small compared to the length. The ratio of R over L is very, very small. So this is R, and this is L. Okay, so what types of symmetries does this solenoid actually have? I mentioned one already, translation symmetry. You can translate it along its central axis. You can translate it along the central axis. Any other symmetries that it has? Yes?
Rotation of our axis.
Rotations. You could rotate it, and you're not going to be able to tell the difference, whether it's rotated by pi over 6 radians or pi over 2 radians, or just kept the same. It looks the same because it has this rotational symmetry about the central axis. Good. So, based on these symmetries, we can argue that the magnetic field inside the solenoid is going to have to point. Well, it's going to have to be axial, like this. Right now, there are, for a finite solenoid, there are these end effects. It does have to wrap back around again. Now, let's say we don't know the field strength due to the solenoid. Well, we can apply Ampere's law to find it. And the first thing we do when we apply Ampere's law is we want to create an Amperian loop. And our Amperian loop should match the symmetry of the current distribution. So I'm going to choose one that matches the symmetry of the field. So I'm going to choose a loop that goes like this. Here's my Amperian loop. The reason I'm choosing it to go in the counterclockwise direction is because that's the direction I expect the magnetic field to go already. If I have a bunch of loops of wire like this, and I use the right-hand rule, my thumb in the direction of the current, the field points to the right through the solenoid. Okay, so now to apply Ampere's law, we just need to basically calculate the left-hand side instead of equal to the right-hand side. So the left-hand side of the equation gives us, well, I have to calculate the line integral along each of these paths. 1, 2, 3, and 4. So the left-hand side of the equation gives me the line integral of B dot ds. This is going to be the integral, and I'm going to call the bottom one here, I'll call this path 1, 2, 3, and 4 together. 1, 2, and 3, and 4 form a closed loop. So it's really, first of all, I integrate along path 1, and this is going to be basically b dx plus the integral along path 2 of b dot ds plus 3 plus 4. I'll keep those all together instead of breaking them up piecewise, because this part of the integral actually has to equal 0. The only part of the loop integral that gives me any contribution is the part where there is a magnetic field. Now, along path 2, magnetic field points to the right, but the path points up. So there's 90 degrees between the two. So cosine of 90 degrees is 0. So that part of the integral gives me 0. When I'm outside, there's also 0 magnetic field for a long solenoid. The 0 magnetic field, remember this is highly symmetric, so it's very, very long. And then this path number 4 also gives me 0 as well. So the only contribution actually comes from this bottom part right here. And if I want to figure out how much that contribution is, I should label how long. You know, I just created this surface, this loop, so I can define its length to be just curvy L. I'll just say it has a length of curvy L. And let's say it also has a width of curvy L. Okay, so then that means that this integral then just equals b times curvy L. Now this equals, according to Ampere's law, the line integral just equals mu naught times I enclosed, so this just equals mu naught. And the amount of current that's enclosed in that loop, or that punctures through that loop, is just going to be mu naught. Now there's a bunch of turns of wire, so I'm going to need here, let's say my solenoid has a turn density small n, which is just the total number of turns divided by the total length. So n is the total number of turns. So the amount of current inside is the number of turns per unit length multiplied by the length, which is L, multiplied by the amount of current through each loop, which is I. And all we do is solve for B, and we get B inside equals mu naught n I. Magnetic field inside the solenoid. So really, just using Ampere's law, we can find it rather, in only a couple steps here. Which, using the Biot-Savart law, would take a lot longer. Well, it would take longer to do it. We'd have to set the big integral to fit this expression here. So interesting things about this expression is it doesn't depend on the radius of the solenoid. I already alluded to this earlier. Yes?
So for a long solenoid, it's not dependent on the number of turns, it's just about the density of them?
Exactly, the number of turns per unit length, regardless of how long it is, how tightly coiled it is. Which kind of makes sense. If I coil it, if the turns are coiled twice as dense, the field we'd expect to be twice as strong, just like as if there's twice as much current going through, we'd expect the field to be twice as strong. Yes?
Will we be required to derive that using Ampere's law on the final?
So you may have examples on, well, you'll have examples on the homework, and there could be a question on the final where you apply Ampere's law to a distribution of current, and you use that to calculate the magnetic field. All right, now, so this is just a simulation of really what I showed you on the board here. You can see that here's my Amperian loop along each of the paths, 1, 2, 3, and 4. And you can see that not all of, actually path 3 has the largest value of B dot ds. The other ones are not exactly equal to 0, and that's because it's not completely square. If I make it completely square, I could probably get it to be 0 here. But if I take that loop and I move it outside the solenoid, right, well now there's, along the total path, the complete path integral gives me 0, and that's because 0 current is enclosed. So it always, what's interesting about this law is that that line integral always just equals mu naught times whatever current is enclosed in there. All right, so if I make it longer, so here the loop integral has a value of 27.25. If I make it longer, that path integral gets longer, and that's because more current is enclosed in that loop. Right? The other way to increase the path integral would be to increase the strength of increase the current. If I increase the current, the path integral grows as well, but mu naught I enclosed will always equal exactly the same as that path integral around the loop. Okay, so the key is, here I chose kind of a funny one. I chose a square loop. That's in particular because I'm looking at a solenoid. And last day we looked at a loop that was a circle because we were looking at a fat wire, right, or a wire that had some thickness to it. Now imagine I take a solenoid, so you have a homework problem like this, and I take the two ends and I connect them together. That's called a torus, or a toroidal solenoid. Now what kind of Amperian loop would you choose in this case? Circle. And the circle Yeah, it would be inside the solenoid. If I took that solenoid and I bent it, attached the two ends together, your loop would want to be, your magnetic field would just be circular in this case. Your loop would have to be inside that loop. Yes?
So when you said like sides 2, 3, and 4 go to 0, for the same thing you put on the computer, they weren't 0?
Because the angle wasn't exactly 90 degrees. So the reason there's 0 here is because that angle, it's exactly 90 degrees. B dot ds, for every element of B dot ds along that path is exactly 0 because the angle is always pi over 2 or 90 degrees. But here I was just trying to manually sort of make it 90 degrees. All right, so the final thing to discuss in this chapter is, well, something we've already seen already, but we've looked a lot at how to calculate magnetic fields. But as far as what do magnetic fields do? Well, what are the effects of magnetic fields? Well, they cause forces, right? They exert forces on moving charges, and this is Lorentz Force Law. So I'm just going to write this on the board. Lorentz Force Law says the force on charge Q is equal to Q V cross B. The magnitude of this is Q V B sine theta, where theta is the angle between V and B. Okay, so when we're dealing with magnetic fields, the force vector is always perpendicular to V and B. Whenever you take a cross product, the third vector that you get lies in a plane that's perpendicular to the first two. Direction is given by the right-hand rule. So let's try an example of this. Let's just warm up here. Okay, so take out your voting cards. Let's say I have an electron moving down, and it experiences a force to the left. What direction is the magnetic field that it experiences? Take a moment to prepare your vote. Okay, so let's take a vote here. 3, 2, 1. Okay, 30 seconds. Convince your neighbor. All right, and let's take a vote here. 3, 2, 1. Correct. It's into the page. So if I point my fingers in the direction of the velocity vector downwards, and then I curl my fingers in the direction of the magnetic field, which is into the board, I get a force to the right, but it's a negative charge.
Oh.
It's a negative charge. But if I multiply this by negative, it's like rotating your vector by 180 degrees, so it points in the other direction. Okay, so there's, as we've discussed, there's different versions of the right-hand rule. You can choose which one you're most comfortable with. The one that I just described here is, so V is you point fingers. And then you curl towards B. And then F is your thumb. Okay, so this is the right-hand rule. Okay, let's look at another example here. Let's say I have a beam of electrons. And I have a magnet as well, which is exactly what I have on the counter. So here's an electron moving with speed v. And underneath this electron, I have a magnet that has a north pole and a south pole. So the question is, which way does this beam of electrons, and let's say it's a bunch of electrons, and they're all kind of, they're moving like this. So which way does the beam deflect? Up, down, into, out. The reason I didn't add right and left in this case is because the vector force that you get is always going to be, if v is in this, if v is already to the right, the force is never going to be in the direction that the charge is moving. That's how electric fields work. That's how electric fields work, but that's not the way magnetic fields work. Okay, so take a moment to quietly predict which one you think it is. Okay, let's take a vote here. 3, 2, 1. Okay, 30 seconds. Convince your neighbor.
So like if you have this way,
All right, let's take another vote here. So, 3, 2, 1. Okay, the majority are saying C, which is correct. It's into the board. And one way I could see that is the magnetic field of this magnet sort of points upwards like this. Okay, so if I have a magnetic field, I have a velocity in this direction, and I have a magnetic field up. For a positive charge, the force would be out. But since it's a negative charge, the force is in. So that gives me this one right here. So here I have a tube and a Tesla coil, and the Tesla coil can produce a really high voltage at one end. And you can see that beam of electrons, which is guided through that small opening. It kind of is glowing there and then being illuminated on the screen. Can everyone see it? Now I'm going to take a magnet. You can see the Lorentz force in action. I can use the magnet to basically steer the beam of charged particles. You can see that the direction that the beam moves depends on the orientation of the magnet. So this force is something we can definitely measure. You can definitely see the effects of it. This is the basis of cyclotron motion. The force is always towards the center. Each thing is going around and around in a circle. Okay, now, so here's the Lorentz force. Now, we've been talking mostly in this class so far about DC or direct current. But as you may know, that the electricity that comes from outlets is AC, it's alternating. Okay, so here's a filament. It's sort of a high resistance filament because if you look at this, it's fairly bright, but it's not so bright that you can't actually see the filament. A lot of filaments are so bright, and then the glass is actually clouded, so you can't actually see inside as well, but the filament is so bright. But this one, you can actually see the two loops. Can everyone see the two loops? Now, if I was to bring a magnet towards a current, there would be a force that kind of bends it, right? Because it's moving charge in a magnetic field. However, you notice something interesting happens here. I get the orientation. I get the orientation correct. I can really make it vibrate. So notice that this magnet is not just pulling on it and holding it in place. It's actually vibrating the filament. And it's vibrating it at a frequency of 60 hertz, which is the number of cycles per second with which the current is changing direction. So the current, the charge inside the wire is flipping back and forth directions at 60 times per second. So now this magnet is going to be pushing on it for one cycle and then pulling on it during the half cycle. And what it does is it drags the filament back and forth and causes it to vibrate or shake. Okay, so we actually have AC current inside the filament here. Is everyone temporarily blinded? You look right at the light. I know I am. I was pretty close. All right, regaining sight. Regaining sight. Regaining sight. All right, ready to go. Still blinded. So, still blinded. Okay.
I see the light bulb in my vision now permanently.
Well, hopefully that goes away sooner than later. Well, we can write the Lorentz Force Law also by replacing the QV. We can replace that with an IL, right? Because these have we talked about this last day, these have the same units. This works well if I just have one charge that's moving with speed v, but if I have lots of charges moving, well, let's just talk about currents instead of point charges. And then it's the same physics. So the Lorentz Force Law tells us, really what it's telling us is the effects of a magnetic field. So let's see if I can demonstrate this here. So I have a wire in a strong magnetic field. And you can see this wire is kind of like a thick piece of tape. I can actually tear it pretty easily if I'm not careful. So I'm going to, because these forces are really small, really what I'm really trying to do is make the current really, really large. If I get a large field with a large current, I can get a force that I can actually see or measure. So this switch here turns on the current. You can see what happens is the force is large enough to actually, right now the tape is just hanging downwards under the gravitational force. But the magnetic force is large enough to actually pick it up. Right, now let's try to understand why the force is upwards. Well, out of the positive terminal of the battery, the current is going this direction. So current is this direction, and the magnetic field it's horizontal, and in fact this is the north, this is the south. So it's current, magnetic field, force is up. So every time I press the switch, I get a force upwards on that wire. Magnetic force actually is much larger in this case than the gravitational force, because it's just a very thin strip. Now, if I switch the direction of the current through the wire, it would basically just push the wire down. Right? So positive charge moving to the right, now I have positive charge moving to the left. Now we know it's not actually positive charge that's moving, it's actually the electrons. But in the first case, positive charge moving to the right is equivalent to negative charges moving to the left. So either way you use the right-hand rule, you're going to get that, force in this case. And we can actually see that force here. All right. So let's say I have some currents. Okay, let's say I have two different wires, I1 and I2, and these are long wires. So conceptual question here is the force. Is there going to be a force between these wires? Are these wires going to attract, repel, or is there no force between those wires? Give you a moment to think about the force between these two wires, what that would look like, and we'll take a vote. And get ready to prepare your vote. 3, 2, 1. Okay, a little bit of disagreement here. Convince your neighbor. Use the Lorentz Force Law. Explain to your neighbor what direction the force will be.
based on, so I2 based on the field lines. For I2, field then I1 from based on the field I2
It sounds like the current is going the other way.
Okay, get ready to prepare your vote. All right, is it A, attract, repel, or no force? 3, 2, 1. All right, we're kind of split between attract and no force. Attract is correct. They do attract each other. Now, why do they attract each other? Well, let's just apply the Lorentz Force Law, and let's calculate the force. Let's say we want to calculate the force on wire number 2. The force on wire number 2, and I'm just going to write the magnitude here, is going to be the current through I2 times the length of 2 times the magnetic field due to 1. Now the magnetic field due to 1 is mu naught I1 over 2 pi, whatever the distance is between them, I'll just call it d here, over 2 pi d. So we could write then, I'll call this little f, I2, which is big F, I2 divided by L2, or the force per unit length, is just mu naught I1, I2 over 2 pi d. Now how do we know it's an attractive force? Because on wire number 1, if we look at the magnetic field due to wire number 1, the current points upwards, so the field circulates around it like this. So on the right-hand side of the wire, the field points into the board. Right, over on the left-hand side, it points out because it wraps around. I'm picturing circles that are kind of wrapping around the wire. So then at the location of wire 2, I have a current that goes upward and a field that's in gives me a force that's to the left. So that force is attractive. So the takeaway message here is, like currents attract, right? We could guess what would be true. And that's different than electric charge in the sense, right? Like charges repel each other, but like currents actually attract each other. Now, by symmetry, the force on wire number 1 is also going to be to the right. It's also going to attract. It's also going to attract, but opposite currents will repel. Opposite currents repel. Yes?
Where did you get little f equals big F over L?
So I just divided this little f, just calling the force per unit length. If I have a really long wire, I might not want to know the force on a really long wire, but just the force per unit length. Yes?
Where did 2 pi d come from?
Oh, so this is B1. B1. Magnetic field due to a long wire.
So where did you get that?
Well, that's what we've had in previous classes. Magnetic field due to a long wire is just mu naught I over 2 pi r.
2 pi r, where did d come from?
That's the distance. D is the distance between the wires.
I thought d was diameter. Okay.
Well, I mean, yeah, just whatever distance it is between the two wires here. Okay, so let's look at now why. Now, magnetic field, just like electric field, is a real physical entity. So here's two wires. Let's look at a picture here, where switch is closed, and those two wires attract each other. Now, what's being sketched in the picture here is the net field. The net magnetic field due to the two wires that actually pulls them together. Now, what's actually happening here is between the two wires, there's called a stress. There's a stress in the field, and that stress puts the field in tension. Right? There's a tension which pulls the two wires together. So as those field lines are changing, they're basically changing because the amount of current is changing. There's more current, the field gets stronger. Also, too, when the wires get closer together, the field gets stronger. So there's properties such as tension in the field itself. Now I'm going to show you another simulation here, which, let's see if this one works. So this is just the case where the current is anti-parallel. You can see that now the field between is being, in a sense, compressed. Right? So if there's a compression in the field between the two wires when they're anti-parallel, that's going to push the wires apart. Okay, so the point here is, what do fields do? What are the effects of field? Well, they exert forces on moving charges, and currents are nothing but moving charges. All right, now what happens if we have, let's say, a loop of current? If I just take a long wire and I bend it into a loop, well, that's very, very similar. Nothing, in fact, is going to change here, because I could either have like loops or I could have opposite loops. So let's look at what this looks like here. So as the current is slowly ramped up, we see that there's a force between these two loops. Now the bottom loop has 3 times as much current as the top loop. That's why those orange dots are moving 3 times as rapidly. Now, which do you think that, well, we can tell from the picture here, but are these current loops like or unlike? They're like, right? Like loops, so that's why, actually, let's look at this again. Like or unlike? Unlike. So, repulsive force. So the field is being compressed in between the two loops, and they push each other apart. Okay, there'd be a force between those two loops. All right, one way to think about this is, for loops, is I can think of it as north. Sometimes it's easier to think about it in terms of north and south pole. So if I think of it as, let's look at some loops. These would be like loops. Now the loop that's on the left-hand side, can anyone tell me what side, if we think of this as a little magnet, What side of this loop is its north pole on? The left or the right? Correct, yeah, the north, this would be like a little magnet where the north pole is on the right side. So same thing with this other loop right here. We would have north, south. Right, so you can see why they would attract. Okay, to actually calculate the force between two loops, you would need to take the magnetic field due to one loop, for instance the left loop, and then every little section you'd have to calculate the force, and it would give you a little force that looks like this. And then you'd have to add up all those forces around the loop. Well, it would be a little force that looks like this, actually, kind of. And you have to add them all the way up around the loop, and in the end, you'd get a net vector that points to the left, which gives you an attractive force between those two loops. They tend to attract each other together. Question?
But we can have to know how to calculate that.
Well, there's examples. There's similar examples in the homework and on some of the practice exams. But I don't think this question is there. Yeah, I don't think that question is not in the homework. All right, now, final thing that I want to discuss here is loops. Well, I'll call it magnetic dipoles. In many ways, magnetic dipoles behave the same way as electric dipoles, because if I have a region of uniform, let's say I have a region of magnetic field, and I put a loop of current into that magnetic field, and let's just say the loop, let me just tilt the loop a little bit. See, so this loop has a certain cross-sectional area. So this is the cross-sectional area. And again, we're going to define an area vector for this loop, because if I move my thumb around in the direction of the current, I get a magnetic field that goes that way. So I'm going to define the area vector to point in the direction of the field. It's normal to the surface of the loop, which here is flat. And this vector I'm going to call mu, which is magnetic moment. Okay, so mu equals IA, just the amount of current through the loop multiplied by the area vector of the loop. Okay, so question is that what direction? Let's say I break this loop into a bunch of little chunks of current. What direction do we think the force on this little top chunk of current is going to be? This top little chunk of current that's coming directly out has an upward force, right? What about this downward section? there's a downward force. So in a uniform field, and we'll end on this. Okay, but if the field is uniform, there's no net force. And the dipole isn't pulled one way or the other. But you can see that that produces a twisting force, like we call it torque. And torque, there is a non-zero torque, and the torque is equal to mu cross B. The torque tends to align B and mu. Right, so you put a magnetic dipole in a magnetic field. That magnetic dipole wants to twist to align itself with the magnetic field. Right, and you can see that that would kind of cause, if there was some damping, it would cause the magnetic moment to kind of settle down toward its equilibrium position, which would be its lowest energy position, which would point in the same direction as the magnetic field itself. All right, so next class we will start, that takes us to the end of magnetic fields, but we will look next class at we'll start Faraday's law and Lenz's law. Your homework is due on Wednesday for this chapter.
Are we getting midterms?
Midterms I'll do back in lab. It'll be easier. In the lab. Yeah. No, I haven't. It's between five. Okay. Yeah.
Average between 20 and 30.